All right. Looks like we're ready to go. The other sheet A, I believe Mark was supposed to be doing this discussion, but it looks like something might have come up. So I'll be leading this section again. So first, we're going to go over a lot of questions over the practice quiz 1. So are there any questions that anybody had when they were doing practice quiz 1? And then we can kind of go over those. If you just want to type in chat, and then we'll kind of go over the ones that most people had questions over, and we can kind of work through those problems. Okay, so it looks like we have one for problem 7. Any others people want to throw in chat? Okay, so we'll just go ahead and start with practice problem 7. So whoever asked that question, do you want to kind of explain like how to tell which of these statements is true? Where were you kind of getting stuck at?
Okay, that was me who asked that. I was just confused because I couldn't figure out how to prove which one was true and which one was false.
Sure.
I don't know how to go about it, really.
Yeah, sure. Okay, so let's go ahead first, and we can just kind of work through this problem. So to negate first, let's just go ahead and negate this predicate statement. So if we want to negate this, that for all x, that's an integer, there exists a y, that's an integer, such that x plus y is equal to 10. So as we negate it, we just got to move that negation through the entire statement. So first, we're going to negate the for all x as an element of z. The negation of that just means that there exists an x, element of z. And then we would have a negation of everything else. Then the negation of there exists a y, an element of z, that would be for all y. And then we'd have a negation of x plus y is equal to 10. And that would be that x plus y is just not equal to 10. The negation that if we have two numbers that equal 10, the negation just, they don't add up to 10. So this would be the negation of our statement right here. And so now the question is, how do we know which of these two statements is true between this statement and this statement? Now here we're not asked to like prove that these two statements are either true or false. Are you allowed to skip this process to immediately negate all three? Yes, you could negate all three. I would recommend doing it one at a time, though. And the reason is you can earn partial credit this way if you show all three of these steps. If you negate it all the way through and you make some mistakes, you'll just lose some point. But if you get everything right, just except the last step, you can earn some partial credit that way. And it's sometimes more helpful when you're starting out to just kind of work through all the problems. Just work through all the steps like this. But yeah, so this problem, we're not asked just to prove this. So we just need to kind of think about it from kind of a logic standpoint. So the first part, let's take a look at if we believe the original statement is true or false, that for every integer, there exists another integer such that x plus y is equal to 10. So for every integer, we can find another one such that if we add it to x, we equal 10. So if you want to type in chat whether or not you think that statement is true or false, that for every integer, there's another integer that if you add them together, then we get 10. Awesome. Yeah, so it looks like there's a lot in chat. And yeah, most people looks like are coming, that the statement is true, and it is true. The reason why is because of all integers. So we can kind of solve the statement as, x plus y is equal to 10. So 10 minus x is always equal to some integer. We know this, and this is true by closure, right? That we can subtract an integer from any other integer and we still get an integer. And so that kind of gives us the intuition behind maybe why this statement might be true. But now let's take a look at, so if we know that this statement is true, well, hopefully the negation of the statement should be false. But let's kind of think about it from a logic standpoint. So with the negation of the statement, we have that exists some integer such that for every other integer, the sum of those two integers is not equal to 10. And that doesn't seem like it would be true, right? And because if we are given some integer, we can always find another integer that will add to 10. So it can't be the case that for every other integer, their sum is not 10. So I know that's a little bit tricky, but it's just kind of thinking about it from that standpoint might help you figure this out. So did that answer, whoever asked that original question, did that answer your question?
Yeah, that makes sense. I think I was just thinking about it kind of differently. Like I just couldn't really tell the difference between the original statement and the negation, like how they meant a different thing, but I get it now.
Okay, yeah, hopefully that kind of clears it up a little bit. Were there any other questions that anybody else had on this problem, on problem 7? No? Looks like we're all good on that. Cool. So it looks like someone else from earlier said that question 6 was another one. Yeah, it looks like there's 2 people who had some problems with question 6. So let's go ahead and take a look at question 6. Yeah, so saying took a long time to brute force the closed formula. And can you do a closed to recursive example? Yeah, so this should, yeah, we could do both if you want. We could find the closed form, and then we could look at seeing if we can find a recursive form, Jake, and then that should hopefully kind of give you an example on that one. So the way you just kind of have to work with these problems, especially to find the closed formula, is you have to just look for patterns. That's really how you solve these sequences problems. And the more and more you do, the more you're going to kind of be able to start picking up on some of those patterns. So first, what I like to do is just to see if there's any simple pattern we notice between the difference between any two numbers. So between 5 and 1, we increment up by 4. Then we increment by 2. Then we increment by 10. And then we increment by 14. And then we increment by 34. So from this kind of pattern, we seem to be kind of growing at what seems like an exponential rate. We kind of have this weird thing where we increase by 4 and then increase by 2. But everything after that, we seem to, from 2 to 10, 10 to 14, 14 to 34, we seem to be kind of growing at exponential rate. This isn't just some simple addition between the two. So whenever we're thinking about exponentials and we kind of notice, we want to start thinking about what are the standard ones that we kind of know about. So, we know like 2 to the x, right? So 2 to the x, that kind of gives us the pattern 1, 2, 4, 8, 16, 32, 3, 1, 3, 9, 27, 81, 4, 1, 4, 16, 64, 256, etc. So these are kind of the standard exponentials that we can kind of think about. And hopefully we can find maybe a pattern between one of these. So does anybody notice maybe some kind of pattern where we could, that that we could use maybe one of these exponentials to find this closed form that's kind of matching close to what we have here. Okay, so it looks like Colby kind of have this idea about doing 2 times 5, 2 times 7. Yeah, that's a little bit close. And there may be something there. Oh, so you're saying 2 times. Okay, yeah. So Colby, you might have found the kind of recursive formula. But first, we'll just try to figure out to see if we can brute force the closed form. Then we'll find the recursive form, and then I can show you that maybe an easier way to find recursive. So yeah, if you use 2 to the x, then it's either adding 1 or subtracting 1. Yeah, so that's a really good observation there that we can make. So yeah, what Nathan's saying is that, well, if we actually compare 2 to the x here, except ignoring this 1 right here, if we compare 2 to the x, the first 2 values, 2 and 1, they're off by 1. You subtract 2 to get 1. From 4 to 5, you could add 1. From 8 to 7, you could subtract 1. From 16 to 17, you could add 1. From 32 to 31, you could subtract 1. So we're kind of noticing that there's this pattern of 2 to the x, but we're adding and subtracting each one at every other step. So what we kind of have then is our closed form is we have this 2 to the n. So, and then we kind of have this add 1, subtract 1. And the way that we express adding 1 and subtracting 1 is that's always a -1 to some power. And we can kind of test this out to see does this closed form that we came up with really work. So a to the 1 is 2 to the 1 plus -1 to the 1. So that's 2 minus 1, which is 1. That works. 2 squared plus -1 to the second. So that's 4 plus 1, which is 5. That seems to work. And if we try the others, this will work. Brendan, that's what I eventually figured out, but I was wondering if there was any faster way of doing it. There is. We can find, if we find the recursive, it's often easy to find the closed form. So we'll take a look at that. But yeah, if you want to try to brute force these, the best thing to do is just to look for those patterns. So you should know what are the patterns of these exponentials. You know, how do exponentials always generally look? And then that'll kind of help you find these closed forms a little bit easier, knowing what, if there's a simple addition between each sequence. So knowing some of those patterns can work. But I guess just as an exercise, let's try to find, this problem didn't ask for this, but I think it might be good because there's some more questions about this. Brendan, I know how to make a recursive formula from a closed form, but not the other way around. Oh, yeah. So yeah, it doesn't always work to come from the recursive to the closed form. You are correct in that. So yeah, sometimes for these closed forms, you do just kind of have to brute force it. So that'd be my recommendation. The problems you're going to see on the homework and on the quizzes are going to be based on either these exponentials or simple kind of multiplication steps or addition steps. So they're going to be patterns that you can hopefully pick up on, and that just kind of comes from practice. But to get that example that kind of Jake was asking for recursive, let's just do this just as an example. So recursive, we always need 2 things for recursive formula. We need the base case, and that's just easy. It's just a sub 1 is 1. And then we kind of need to figure out this kind of recursive form. And it looks like Colby kind of had a guess earlier. What they noticed is between these values here is that there's this kind of relationship that if we take 5 times 2 minus where 5 times 2 is 14, and we add 3, we could get 17. 2 times 7, or 2 times the previous value. So what he's kind of suggesting here is that 2 times the previous value, and then plus or minus 3 is what could give us these values. So for example, we could take 2 times 1 plus 3 is 5. 2 times 5 minus 3 is 7. 2 times 7 plus 3 is 17. And so Colby just kind of picked up on that pattern, and that works great. If you kind of catch that pattern right out of the gate, that works. In general, this will be 2 times a sub n minus 1 plus negative plus 3. Where'd my writing go? It looks like my stylus just gave out on me. Let me see if I can fix this. Yeah, sorry, 1 second. So if you just want to kind of, what you could do while you're waiting is you could think about how we could come up with that recursive formula from the closed form that we just found. And then let me see if I can get my stylus to work again. Okay, I think I have it working again. So let me see if I can share the screen and if it'll work. There we go. So yeah, so in general, this would be 3 times negative 1 to the n. But like hopefully some of you were working through, we can do this from the closed form. And so if we know the closed form, like we were kind of talking about, it's easy to find. So the closed, what the recursive form is. So the closed form is a sub n is 2 to the n plus negative 1 to the n. And then to find the recursive, we can just use this closed form. So the way we do it is we solve for what's the n minus 1 term using the closed form. So that's 2 to the n minus 1 plus negative 1 to the n minus 1. And then what we kind of want to do is we want to somehow find this value in our a sub 1 term. So that way we can do a substitution. So does anybody want to say how we could rearrange, either in chat or just by raising your hand, how we could make a substitution to solve for the recursive form in here? If someone wants to kind of raise their hand for what we could do. Oh, sure. It looks like, so Jackson, you can go ahead if you kind of want to explain how you did it.
Well, I know what to do, but I don't know how to do it. So I know there's a property about n to 2 to the n minus 1 where you can separate those into 2 different exponentials. I just can't remember what it is. If it's 2 to the n times 2 to the minus 1, or if it's I just can't remember.
Yeah, the trick here is it's actually kind of it's 2 to the n divided by.
Oh, It is what I thought it was. It's just simplified. Okay.
Yeah, the reason why is because if you kind of think about this from an exponential point, it's like we kind of factored out like a 1/2 from this 2 to the n minus 1. So if you factor out the 1/2, you need to add a 2 into it. And so that's just kind of a quick, easy way to kind of remember how that works for that one. And then you could do the same for this one, -1 to the n, and this would be divided by -1 because it's kind of like you factored it out. Yeah. And then so 1/2 times 2 to the n minus -1 to the n. And then what were your next steps that you were gonna say?
Move the 1/2 over, and I don't know, you need a plus sign again somehow. Maybe take out a -1.
Yeah, we could take out a -1, so then we'd have negative. How do I?
Would it be -1/2 times 2n plus -1 plus 1? Then I don't know. I think I did it wrong.
Okay. Yeah. Anyone else? The negative.
Sorry.
So Brendan's. Oh, no worries. You're good. No, these problems are sometimes tricky. So Brendan says, to the n divided by 2, the minus sign would become positive if we take out the negative. Right. This minus sign here would stay a negative because you kind of like factored out, you kind of pulled out an extra -1. Let me think about this one some more. I'll update the scribbles later for how you can do this recursive. I'm blanking a little bit right now off the top of my head to get this one. It's a little bit trickier than I kind of had anticipated. But I'll update the scribbles for all of you later when I go ahead and post this. That way we have some time to get to some other questions. And there's a proof problem that I really want to make sure we have time for. Yeah. So everyone, so they're, you can, like Colby and Brendan are saying, you can, pull out that -1 all the way through. But the issue is you're going to end up with the minus in front of this 1/2, and I was just working to figure out how to do that. But we'll go ahead and move on to another problem because I want to make sure we definitely have time to get to the proof problems because those are going to be really beneficial for some of the later homeworks to do proof example. But were there any other quiz questions that I could answer? So we did 7 and 6. Any from the first 5 that anybody had any questions on? No other questions on the first 5? Cool. So we'll go ahead and work on if there's no other questions, then we can go ahead and start work on this problem on proof by cases. So this should hopefully help you if you've seen lecture 4 on some of the introduction to proofs. This will be a really good problem to get just some more practice for some of the later homeworks on how we can do proofs. So the problem here is, so we're asked if n is an integer not divisible by 5, then we're supposed to prove that n has a square that is either of the form 5k plus 1 or 5k plus 4. So I want everyone just to take a minute to kind of think about this problem and think about because we're asked this problem to be a proof by cases. So what kind of cases might we be looking at for this problem? So just go ahead and take about a minute to kind of think on your own about how we can maybe start with this proof. Okay, so hopefully you've had a time to kind of think about how we could start. So what are kind of the cases that we're going to be looking at if someone either wants to type in chat or raise their hand to explain what their thoughts are for how we might start this proof? So we got some suggestions. Look at the remainder. We write the pattern, even or odd. Yeah, all good ideas. So the one we're definitely going to be looking at, yeah, some more suggestions. Yeah, we're looking at the remainder, right? And Nathan's perfect here. If a number ends in 1, 2, 3, or 4, are going to be the cases. And so let's kind of think about why that is. And the reason is with our proof here, whenever we start our proofs, we assume that the hypothesis we're given is true. In other words, our hypothesis is n is an integer that's not divisible by 5. So what does that mean, right? That means that by the division theorem, when we divide, the remainder is going to be not 0 here. So in other words, to start this proof, we could say let n be an integer given. That's not divisible by 5. And then, like some of you were suggesting in chat, we're going to look at that remainder when it's 1, 2, 3, or 4. But we need to explain why that remainder is the way it is. And so we do that by the division theorem. If you remember what the division theorem is, it says that any integer a is equal to b times q plus r, where r is less than that q value that you were dividing by. So by the division theorem, so then the remainder when n is divided by 5, when n is 1, 2, 3, or 4. And so these are all of the cases that we're going to have to consider. That we have these kind of 4 possibilities for the remainder. If we have some integer not divisible by 5, we could either have remainder 1, 2, 3, or 4. And for all of these 4 cases, we need to prove that the square of n is of the form 5k plus 1 or 5k plus 4. Why not 6? Great question. Yeah, great question, Jackson. Why not 6? So maybe one helpful side note here is let's recall what the division theorem is. So the division theorem says basically if I have some integer a, then a is equal to b times q plus r, where b is an integer, and then r is less than b, excuse me. Less than b. And if you want more help on this, I believe this is also stated in the textbook. on page 103, if you have that, and you want to look at the definition, kind of some more explanation there. And so what this says is that our remainder is bounded by whatever number we're dividing by. So if A is divided by B, then we can rewrite A as this. And like someone is suggesting, like Brandon suggested, if we had a remainder 6, we could divide by 5 again, and you'd end up with the remainder 1. This is kind of like that idea of having a modulo, where you just take the remainder, where you can take 6 mod 5 is 1, is the same as 1. So remember that modulo is just the remainder from division. And that's why it wouldn't be possible. The division theorem also tells us that it wouldn't be possible to have a remainder greater than what we're dividing by, or greater than or equal to 5. And it's called the division theorem. I guess I just don't get how remainders get us to those two formulas. Do you want to unmute yourself and kind of explain what two formulas you're talking about here?
Just the 5k plus 1 or 5k plus 4.
Oh, we're going to get to that. So that's the part we
Yeah.
haven't got to. We haven't even started the proof yet.
I just didn't know how people are like instantly like remainders. That's how you do it. Because to me, it was like I have two formulas that I'm trying to get two like even and odd. It just seemed like that's what I would have done and probably would have been stuck for ages. So I don't know how people just knew it was the remainders.
Yeah, so the trick to finding out the remainders is from our hypothesis, knowing that we have an integer not divisible by 5. So if we have an integer not divisible by 5, then that integer has to have either one of these 4 remainders. It either has to have remainder 1, remainder 2, remainder 3, or remainder 4. So it's from our hypothesis statement that we can kind of figure out we need to look at the remainder. Just because we know we just needed to kind of open up this definition of what does it mean that an integer is not divisible by 5. Where an integer not divisible by 5 means it has remainder 1, 2, 3, 4, 4 when divided by 5. And that was kind of the clue there. So yeah, so we've got these kind of 4 cases that we need to deal with. Matthew had a question here. So can you explore the properties of what you are given and hope something stands out? Yeah, or the kind of idea here is really to open up the definitions. Like, what does it mean to say that an integer is not divisible by 5? What's the definition? Kind of is kind of how I like to think about it for this. And this is going to be true in any proof that you do, basically all through college. Any proof you're given is going to be open up these definitions. And so I kind of like to think about this as a definition that you need to kind of open up. And meaning an integer is not divisible by 5, it's got to have remainder 1, 2, 3, or 4. Does it mean 5L plus, well, or L300? Not quite. But we'll get to kind of more on this problem in just a second. So yeah, so now we can kind of start the cases. So we know that we have these 4 cases that we need to consider. So let's go ahead and start with our case 1. And for case 1, we want to say that the remainder is 1. In other words, that n is equal to 5q plus 1 for some q that's an integer. And we're getting this just from the division theorem that we just wrote on the previous page. So if you want to go, I'll go ahead and kind of, I guess I'll get started you with, we'll work through this case 1 together, and then you can spend some time working on how we do the other cases. So here is our case. We want to let n be this value. And then the problem asks us, then we need to prove that n has a square that is either the form 5k plus 1 or 5k plus 4. So we need to square n and kind of see what we get. So if we take n squared, then that's 5q plus 1 squared And if we work this out, that's 25q squared plus 10q plus 1. And then if we notice here, remember, we're searching, we want to prove that this is either of the form 5k plus 1 or 5k plus 4. So we kind of want to factor out a 5 and have some remainder left. So here we've got the plus 1, so that's looking good. And if we notice, we have this 25q squared plus 10q, so we can factor out a 5 here. And that's 5 times 5q squared plus 2q plus 1. And then this is, we could call it 5k plus 1, where k is an integer, by closure properties, by closure of addition and multiplication. Because we were given that q was an integer, we know 5 is an integer, 2 is an integer. By closure, this gives us another integer. And this is exactly what we wanted to prove. For case 1, we wanted to prove that n has a square that's either the form 5k plus 1 or 5k plus 4. We proved here that it has the form 5k plus 1. So now if you all want to take a few minutes and kind of think about how we could solve the other cases. So go ahead and work through case 2 on your own, that n would have remainder 2. Sorry if you said this, but why did you square n? Great question. We squared n because that was what we were trying to prove here. So we were asked if n's an integer not divisible by 5, then n has a square that is either the form 5k plus 1 or 5k plus 4. So we wanted to prove that if we take n squared, we get something of either this form or this form. And that's why we looked at the squared value. So Brennan has a question, if we just write by closure without writing addition and multiplication, is it still correct? Not quite. You need to, we just want to be explicit about what closure properties that we're using at each step. And this is both closure of addition and closure of multiplication. And the reason why we want to do that is because some operations don't have closure, right? Like division. If you do that operation, it's not closure. If you take 2 integers, divide them from each other, you're not guaranteed to get an integer. So we just want to make it explicit so we know exactly what properties we're talking about. Is squaring also closure by multiplication? Yes, it is. So squaring is just equivalent to a lot of multiplication, and that's closure of multiplication. Then it looks like Jackson has another question. Do we need to redefine variables for each new case? Yes, you do. The way you can think about it is it's kind of like a program in a way, in that all of the variables we define in case 1 are all scoped to case 1. That's their variable scope, and outside of that case, they don't have any meaning. So for each case, we kind of need to redefine what those variables are because they're different. It's fine if we reuse the same letter here. So like in case 2, we're reusing this q, not necessarily the same q as up here, but we're redefining it to say case 2 n is equal to 5q plus 2 for some q is an integer. So you can use the same. So you don't have to use new letters, but you just have to make sure you redefine what those variables mean in each case. So you would have to say, you couldn't just say that the n is equal to 5q plus 2. You need to redefine that q is, again, just some integer to make sure we know we're not talking about the same q as in case 1. So good questions. So hopefully you've had some time to kind of think about that one, and we can go ahead and walk through it. So for here, if we have n squared, then we've got 5q plus 2 squared. And then squaring this is 25 q squared plus 20q plus 4. Like we did in case 1, we can factor out the 5. 5 times 5q squared plus 4q plus 4. And that's 5k plus 4, where k is an integer. By closure of addition and multiplication. So any questions doing this next case? For case number 2, it follows pretty similarly from case number 1. But here we wanted to show, again, we remember we want it to be 5k plus 4 or 5k plus 1. I don't remember the question, but I think case 3 proves it false. Let's go ahead and check. Let me get another blank slide here. So case 3, we have remainder 3. So n is equal to 5q plus 3, where q is an integer. And then we just do the square of n again. So that's 5q plus 3 squared. That's 25 q squared plus 30 q plus 9. And this is a little bit tricky, this case here, because we could just follow like the previous problems, factor out the 5, and we'd end up with 5k plus 9. And that's not what we wanted. We wanted 5k plus 4 or 5k plus 1. But the trick here is we can use the division theorem to rewrite what 9 is equal to. So we can rewrite 9 using the division theorem. If it's like if we took 9 divided by 5. So we can rewrite 9 as that's really just 5 plus 4, right? And now we can factor a 5 out of this grouping. And that's 5 times 5q squared plus 6q plus 1 plus 4, which is 5k plus 4, where k is an integer by closure of addition and multiplication. Never would have thought of that. Yeah, this part's a little bit tricky here. Where you could just end up with 5k plus 9 and think it was false. But yeah, this is the trick. Whenever you're kind of working with problems that involve division, the division theorem, you always want to think about where you want your remainder, what range you want your remainder to be in. And so here we knew that we were trying to search for something that looked like 5k plus 4, 5k plus 1. So you're trying to get some value less than 5, and we knew we were dividing by 5. So this is kind of a little trick that we can do in order to show that we end up with 5k plus 4. And then if we do case 4, we're going to get a similar thing again. So if we do case 4, n is 5q plus 4, where q is an integer. So we have n squared, 5q plus 4 squared, 25q squared plus 40q plus 16. And then if someone wants to type in chat or raise their hand, how could we rewrite this? This line here to get what we want. Yeah, so David's saying we could actually take 16 and we could rewrite 16 as 15 plus 1, which is perfect. Just to kind of refresh, kind of thinking about the division theorem again, we can use the division theorem to rewrite 16 as really 5 times 3 plus 1. It's kind of a way to think about it. Now we can factor out the 5. So we get 5q squared plus 8q plus 1, or plus 3, plus 1. And that's 5k plus 1, where k is an integer by closure of addition and multiplication. And that's exactly what we wanted to show. And so now we've shown all 4 of the cases. We proved it if it had a remainder 1, if it had a remainder 2, it had a remainder 3, and it had a remainder 4. So now we just need to briefly summarize everything. Yeah. So one sec, just to answer a question. Jerica, when we write 5 times 3 plus 1, do we need to use the division? Yeah, that would be great to kind of write your steps, especially when you're using the division theorem there. So we could just write here, say this is by the division theorem. And then here we could say that this is by the division theorem. So yeah, I think that'd be great. And then Jake asked question, if any remainder was false, would the proof be false? Yes, it would. That's a great question. So if we found for some remainder, we didn't end up with 5k plus 4, 5k plus 1, like we ended up with 5k plus 2, then the entire proof is false. The entire theorem is false. Because we were asked to prove for any n not divisible by 5. So when you're doing these case statements, as soon as you find one case that doesn't work, that means that the theorem is false. Which is why we have to prove that it's true for every possible case. So that's why you have to go through all 4 cases, because we have to prove it for every possible case, and only then do we know that the statement is true. Have we had any questions, or the proving question ends up being false? No, usually when you're asked to prove a proposition, it'll be true. It'll often ask you, sometimes you might get a question, decide whether the following statement is true or not. If it's true, prove it. If it's false, we provide a counterexample. And this would be like coming up with a counterexample. If you found one of the cases that didn't work, that would be your counterexample to disprove the theorem. And then do you need to write like a final statement? Yes, that's a great question, Jake. So yeah, so then at the end we could write one final statement. So there, like, just to kind of close up, show we proved all 4 cases. Therefore, like we have shown that in all possible cases, for n not divisible by 5, n squared is of the form 5k plus 1 or 5k plus 4 for k that's an integer. And then we could write, either like a QED symbol, or I just do like a box at the end, just concluding our proof. And so we're right at time here. Does anybody else have any last minute questions before we go?
During the quiz 1 review sessions, are we just going over practice problems or the quiz 1 practice problems?
You could either really be both. It really depends on what students need. So if you have questions over the quiz 1 still, you could bring those, or you could go over some practice problems as well. And so just as a reminder for everyone, there's review sessions tomorrow. If you look at one of the announcements, there's like 3 sessions tomorrow. Let me look at the time. So there's some from 10 to 12 with Zoe. Mark has some, I believe, as well. And then mine are going to be Monday from 3 to 5. And then the quiz one will be on Tuesday. So definitely go to those if you have more questions on getting ready for quiz 1. Also, there's some more practice problems in this discussion that we weren't able to get to. So you could also go and look at some of these if you want some more problems on proofs and stuff, on finding the inverse of this statement, and problems on predicates, and on some problems on implications. If you want some more practice, I'd recommend going through those as well. Awesome. So we'll go ahead. Are these slides on Canvas? Yes, they are. And I will post the scribbles later today, and I'll go through that recursive problem and show the steps for that I wasn't quite able to get all the way through here. So yeah, you can look for those later. Awesome. Well, thanks everyone. And we'll go ahead and stop right there.